Okay, thank you, Mr. Chairman. First of all, I would like to thank the organizer for the kind invitation. The title of my presentation is Estimation of the Dipole Polarizability for Excited States. Now, dipole polarizability of the electronic ground state is an often studied molecular property. The knowledge of the polarizability, a tensor, is necessary in our understanding of many various physical-chemical phenomena, like intermolecular interactions, for instance. Now, theoretical calculations for small systems, like closed shell atoms, can be performed to astonishing accuracy. For larger systems, we can use a lot of approximate but accurate methods. We can build models. We can use dipole polarizability for interpretation. In short, the dipole polarizability is a well understood property with a very large pool or database of values of data. Now, the case of excited state is quite different. Both experimental measurements and theoretical calculations are rare, and existing calculations are challenging and difficult to perform. So, for small systems, there are some benchmark calculations published recently, and the worth mentioning is the equation of motion coupled cluster formalism developed and implemented by the group of Anna Krylov. The second one is the algebraic diagrammatic construction formalism that is still, I guess, in the form of the preprint, sorry. And we can also use CAS-SCF, CAS-PT2 wave functions for excited states. But for larger systems, these methods are too expensive. So what's really needed is a simpler approach. Simple but robust approach is what we need. And now time-dependent DFT has become almost a black box for analyzing, for studying excited states. So the combination of the standard time-dependent DFT with the well-known numerical technique like finite field seems to be a promising approach, and it was actually tried several times in the past. The great advantage of this combined time-dependent DFT finite field method is that it's almost no implementation. So the additional computational cost is minimal. We have to repeat our time-dependent DFT calculations. And it's, in principle, it can be applied to very, very large systems. So that's the first part of my talk. It's about static excited state polarizability. Now in the second part of my talk, I will concentrate on the dynamic polarizability for excited states. And for this purpose, we use the CAS-SCF wave functions in the framework of the so-called complex polarization propagator. Okay, so here is a very convenient and very easy introduction of the notion of definition of dipole polarizability. It's a basis for static case, is a basis for all these finite field manipulations. Now, we use standard time-dependent DFT method. So what we have to choose is we have to choose functionals. Now, the choice of the best functionals for molecular polarizability is not so many functionals that the choice is actually a non-trivial task. But recently, both Tucker and Head Gordon tested about 60 functionals for large number of molecules, small molecules, and their findings are that among the among the best performers are the functionals that we use in our, that we also use in our in our calculations. Namely, there is this global hybrid meta generalized gradient functional of trueR, MO6 to X, and two long range corrected functionals, Coulomb attenuating methods bis-relief, and this functional of Head-Gordon. So we use these three functionals. We use basis set pole designed by Sadley, designed especially for electric properties. And we use standard popular software, Gaussian and for time-dependent DFT, and Dalton for CAS-SCF calculations. Now let's move to the static case. Let's start with the uracil molecule. It's obviously a molecule of great biochemical interest. Here we have geometry, and the base is the same as the paper, the benchmark paper of Krylov. And here we have some results. First, let's take a short look at the results for the ground state. We see that our results, our DFT results are, all results are close together. They are in the range of these results is very narrow. And then we perform the calculations, finite field calculation for the first excited state of the n pi star character. And we see that the dipole moment is now down by about 50%, and the polarizability also is slightly up, and the results are similar. They are close together. So how do we compare to the benchmark calculations? Now, first, here we compare to the coupled cluster calculations of Krylov, and we see that we are in very good agreement for the dipole moment, and even probably better agreement for the polarizability. Now, this agreement is surprisingly good. And if we take a look at this ADC results, which come in two models, ADC2 and ADC3, these models differ in their answers. Obviously, this ZZ component, it's physically describing pi electrons, looks too small. Definitely, it's suspiciously low, and so from now on, I will concentrate on comparing only to this coupled cluster calculations. ADC still is not very reliable, I think, because this situation happens again and again in other examples. Now let's take a look at the second excited state. Again, this situation is clear, and our calculations agree with each other. And if we compare to the results of coupled cluster, the agreement is also very good. If we go to the triplet excited state, well, the situation is also satisfactory, at least. I would say it's even, the agreement is really very good. Now, so to conclude the story about uracil, uracil is well described by our method. The excited state polarizability of uracil, both singlet and triplet, polarizability is well described by our method. Let me go to the diazine molecules. Let's go to the first one, pyrimidine. Here we have the results for the ground state and the results for the first excited state. We see that the dipole moment now is almost 1/4 of the dipole moment of the ground state. We see the increase of this in-plane component. And if we compare to the results of a couplet cluster, again, we see that the agreement is good. Okay, maybe let's skip this tetrazine because the situation is not very different here. And let's go to something more challenging, more difficult, namely the molecules of para-nitroaniline. This molecule is often used in nonlinear optics measurements, and its chemical derivatives of these molecules are often used as a new materials for NLO applications and so on. We see that this is charge transfer going on from donor to acceptor group, and is in this orientation is the z-axis. Okay, so it's a charge transfer along the z-axis. So let's see how we fare for para-nitroaniline. We see that this excited state, we see the increase, dramatic increase of the dipole moment. Now the dipole moment is over 12 dBs for those who prefer these old-fashioned units. And we see that this Z component along the charge transfer axis, now our functionals differ a little bit. Well, maybe not a little bit, differ. So if we compare to couplet cluster, we see that the dipole moment is, excited state dipole moment is reasonably well. Here we have good agreement, here you have good agreement. But unfortunately, this charge transfer component is really, we are off by about 25 or so percent. So it's not a very accurate description. If we go to the triplet excited states, situation is even worse. Now it's a complete failure. Our functionals do not agree on the even the magnitude or of the polarizability of excited states. And if we compare it to couplet cluster, we see that we are that's a failure. So we can conclude that this part that for valence excitations, our combined time-dependent DFT FF finite field methods works well, but for systems like dominating by charge transfer, one should be cautious because we can have a problem. Now let's switch to the dynamic polarizability. Let's start with general expression. In this expression, this factor is responsible for taking into account the finite lifetime of the excited states. And if this parameter is really included in the formulas, even in the very practical, approximate way, we have two advantages. First of all, we avoid divergences and resonances. And secondly, from the very beginning, our dynamic polarizability is separated into two parts, imaginary part and real part. An imaginary part is responsible for absorption, real part is responsible for dispersion properties. So let's go quickly to our first example.
Tadeusz, you've done 15 minutes. You're into question time.
Oh, okay. So just let's results for water. I just want to show you that the excited state polarizability of singlet and triplet state of water is really dramatically different from the ground state. We have this average dynamic polarizability for plotted here, two curves, imaginary and real part. We can also calculate the linear absorption cross section. And finally, we can also use a dynamic polarizability at the imaginary frequency to calculate the leading term for this long range part of the dispersion energy, 6 coefficients. So for the ground state, just to check the reliability of our approach, we have, that's experimental values, that's our CAS value. Now the values for excited states are quite large and they are given here. So in summary, combination of time-dependent DFT with functionals like CAM, BC-LIP can do a good job for low-lying valence excited states. Some states like charge transfer dominated states in para-nitroaniline are difficult, so the polarizability is less reliable. We can also use CAS SCF and within the framework of CPP approach to have a dynamic polarizability for excited states. And well, the collaborators in this work, the president is Grzegorz Skrzyński, my Master of Science student now in Katowice, and help from my former Master of Science student, Joasia Kauczor, is also needs to be acknowledged. And well, thank you for your attention.
Thank you very much. We do have a couple of minutes for questions. Are there any questions? I think that there is a lot going to appear in the future in DFT for long-range interactions. Do you think that these improvements are going to be useful for your work?
I think so. Here, our goal was not to choose the best functional, but to see if, say, average functionals work well for polarizability for all systems. But yes, I think that long range, like charge transfer interactions need better functionals, and I'm looking forward to use it.
Are there any further questions on this work? If not, I'd like to thank Tadeusz